presentation will be the drive-by-wire go-kart. Presenters will be Mike Modescu, Nilesh Patel, Pietro Condello, and Tony Liang.
Hi everyone, my name is Tony Liang, and my group members are Pietro Condello, Nilesh Patel, and Mike Modescu. We're going to talk about our project, drive-by-wire go-kart. Well, first I'm going to introduce you what is drive-by-wire system and the future of drive-by-wire systems. What are the benefits of drive-by-wire and our project go-kart and the goals of our project. Okay. Traditionally, in regular cars, you would see the gas pedal is connected to a mechanical linkage, and the linkage would be connected to the engine. With the drive-by-wire system, you would see all these components, mechanical components removed, and use electronic sensors instead. And here, this is a concept vehicle. It's third generation, called GM's Sequel. Uses fuel cell technology and has in-wheels motors, which is controlled by a computer and drives individual wheels. This body is a standalone system. Doesn't even really can put on any frame on top of this standalone base. Standalone base. Any body can be put on top, so therefore you can save a lot of space. There's actually no transmission. It's actually one-wheel drive to all-wheel drive. There's more inside each wheel, and anything can be on top. So that vehicle, and that's one of the benefits of the drive-by-wire system. So drive-by-wire system can reduce emissions by all these electronic components, no more mechanical heavy linkages, and you use these precise electronic motors and sensors instead. This will improve the handling and braking, and importantly engine efficiency, because these are circuits smaller and lighter and space efficient. So how is this drive-by-wire system going to be in our go-kart? So we're going to be replacing all these mechanical systems that were originally on this go-kart, and we'll replace them with sensors and motors, DC motors. There are going to be three main systems. There's going to be the steering system, the brake system, and the drive system. They will all be replaced with all these electronic components. So why did we choose our project? All of us in our group have an interest in automotive systems, and we wanted to apply our electric knowledge into automotive system. So we wanted to simulate a go-kart with this electronic drive-by-wire system. So these goals can be used for this go-kart can be used in many industries, such as old people's scooters, factories, any kind of industries. And the benefits, of course, we want this project to be zero emissions. So I'll introduce Pietro and Johnson at the go-kart.
So once we had the idea that we wanted to implement the drive-by-wire system, we decided a go-kart would be the most cost-effective way to actually get it implemented and have it presentable. What you see here is what we originally started with. The original frame had originally a 36-volt motor implemented to replace the gasoline engine. There was an original disc brake that we later transformed into an electromagnetic drum brake, and there was an actual steering column with an actual steering wheel that was later changed into a DC motor. We toyed around with a few ideas on how to move the steering column with respect to the command input that's sent by an electrical signal, and we decided the best way to go would be direct coupling the motor to the steering column, and it was a 12-volt DC gear motor that was coupled to the steering column, That motor was a good choice because it has the gearing built into it as opposed to having a separate gearing, which may cause reliability problems. So as you can see, the original steering column was cut down and the DC motor was put in its place. One thing that we kept in mind right from the beginning that we wanted, especially our steering system, to be fail-safe. For example, under any situation, if the steering input was lost, we wanted to ensure that the drive controller would shut off, that there would be, under no circumstance, our original design specification indicated that under no circumstance should the driver be able to drive the go-kart without steering or braking control. Both of them would have to be active and fully functional for the drive to be enabled. The steering input comes from a video game steering wheel, and it was modified to produce a pulse width modulation position signal that would be relative to the position of the actual steering wheel itself. And of course, a command wouldn't be of any use unless there's some sort of feedback to indicate what exactly where exactly your position is relative to what you've commanded. And that position feedback comes from a multi-turn potentiometer that was, as you can see, directly connected to the motor that gave a linear output that was proportional to the actual angular position of the motor. And the DC motor was controlled using a Robotech AX2550 motor controller. Our one safety implementation of our design was we wanted to ensure that the motor would not turn farther enough that it would break the tie rods on the steering column. The motor doesn't know exactly when it reaches its limit unless it's programmed to know so. That can be done by software. It can also be done by hardware as well. We made sure we wanted to implement a hardware limit switch that would ensure that the steering would never go beyond its extremities. And this was done by a limit switch using a relay that would open a normally closed contact that would break the path of the steering motor. So as soon as the limit switch was hit, the motor would immediately shut off. But we didn't want to permanently disable the motor because you still want to be able to change the direction in the opposite direction. So we had a diode that would allow, this was a high power diode that would allow the motor to reverse in the opposite direction. All of the internal workings inside the original steering wheel were removed and the electronics were replaced. We needed to produce a pulse width modulation signal that would convert the steering wheel position into a variable width duty cycle. And this was done using LM3524 IC. And it was determined that a 1 millisecond to 2 millisecond pulse width would determine the fully left to fully right, and a 1.5 millisecond pulse width would determine the dead center. And this is a closer detail of our steering system. What you see here in the block diagram, the dashboard is the actual motor controller. This consists of a summing block which subtracts what you've actually commanded with regards to what you've actually, where you actually are in terms of angular position. And that will produce an error signal that will be greatest when there's the greatest difference between what you've commanded and where you actually are. That signal will be sent to a power amplifier, and the greater the difference, the more power that is given to the motor. As that difference decreases, the power to the motor decreases, and the error will become 0, and you will be at where you've commanded. And through a gear reduction, we have the servo potentiometer feeding back to the input. One problem that we did encounter, the original 36-volt 500-watt electric motor that we had implemented, after adding additional weight, it turned out that was insufficient to drive the motor at a reasonable speed. So that was later replaced with a 24-volt 1100-watt DC motor, And once we implemented that, we did find that it was enough power to drive the vehicle. Another safety consideration that we had to keep in mind was the accelerator pedal and the braking pedal. There was no cables of any kind. Everything was all done by electronic components. So of course, a potentiometer would be the obvious choice to use as a sensor for the where you're actually the pedal actually is. We used a military spec potentiometer to ensure that, most importantly, the braking signal would never be lost. And we did find that that potentiometer was strong enough that there's a very little chance of it breaking. And the controller that drives the rear wheels is Advanced Motion Control 120A10. It's a servo amplifier. The company Advanced Motion Control was generous enough to donate 2 of these controllers for our use. And Mike will explain our drive design.
Okay, our drive design, we use the tachometer to feedback the voltage, and is connected to a Schmidt trigger, which when the Schmidt trigger was programmed and the threshold is reached, then the circuit will toggle. That output from the Schmidt trigger will disable the forward and reverse switch, which in turn, when the motor is driving, you will not be able to switch direction of the motor. You will not be able to go reverse if you're going forward. Also, another Schmidt trigger was implemented for the brake pedal. When the brake pedal reaches a predetermined threshold, the Schmidt trigger will toggle and it will disable the drive input. Therefore, when you're pressing the brake, you will not be able to press the drive at the same time, as the drive motor and the brake motor are individual and separate from each other. And I'm going to explain a basic block diagram. This is our brake input right here. Our reference is 36 volt. This is the military spec potentiometers that we were using. It goes through the Schmidt trigger circuit. It goes through an amplifier to turn on the relay. This relay is used to disable the gas input, which is the same potentiometer used, the same input reference voltage. The reference is fed into the relay, and when the brake is pressed, then the gas is disabled. The gas reference input is disabled. Here we have our tachometer, which tells us the speed of the go-kart. It's also fed through a Schmidt trigger, and the Schmidt trigger output is inverted because it's negative. The Schmidt trigger output turns off the 555 timer. The 555 timer takes care of the forward and reverse switches, which is connected to the JK flip-flop. When the 555 timer is disabled, no input from the forward and reverse will switch the output of the JK flip-flop. The output of the JK flip-flop is connected to the transistor amplifier, which also goes to a relay. This relay will take care of the forward and reverse reference input. The same one reference input from the gas pedal is fed through the relay, which takes care of connecting the reference input either to forward or to reverse. We also implemented a brake light, which comes from the same Schmidt trigger from the brake reference input, connected directly to the transistor amplifier. The transistor amplifier turns on a relay, which the relay turns on an LED brake light that we implemented. Alright, our brake implementation. As Pietro said earlier, this is our, we used a drum brake, an electromagnetic drum brake was used. This initially is made for trailers. Therefore, the hub, the brake drum has a hub on it initially, where the wheel goes from the trailer. We couldn't use that, so therefore we machined the hub down, and we ended up welding it to the existing disc brake. because the inside diameter of the drum brake is larger than our outside shaft diameter, drive shaft diameter. The internal part of the drum brake, as you can see it here, is welded to the frame of the motor, which is stationary. You can see the brake shoes here. The insides of an electromagnetic brake drum is very similar to a mechanical brake drum. And the only difference is the electromagnet right here, which when it energizes, it pushes the brake shoes to the outside to the brake drum. Okay, the braking implementation is very similar to the drive implementation. We did use the same military spec potentiometers for the brake pedal, which in turn provides the reference input. The same controller as the drive controller was used, but this controller was used to convert the reference input voltage to a current output voltage, which is connected to the coil. The coil, when you vary the current in the coil, it will either energize or de-energize, more or less, depending on the current output, which in turn varies the braking force. And Elish will talk about our safety features.
Safety was the main concern for our project. We've taken several implementation to make sure that our car is safer. This is one of the designs that we implemented. We used 3 separate buttons for each individual control, for steering, for brake, and drive. They're all momentary switches, and we use the flip-flops so that they can latch, and that will goes to the controller to command the drive motor or the steering motor or the brakes. We also use the AND and OR gate to make it more safer, so that if you were to have gas going when there's no steering input, that showed into a table in the slide. As shown here, in order to have drive on, we have to have all the inputs to be high. So if there were not to be a steering control, the drive wouldn't go on, and the brake would always be there to have it safer. So if you were to fail the steering and the drive, you were to have brake all the time. These are the buttons that we implemented onto the steering. Also, the forward and reverse LEDs were put there so that the user can see which mode they're in, and also we put a headlights on-off switch. And we also have on the steering wheel indication to know if the user is in which, if the functions are on or off, so that they can see. Problems that we encountered were the controllers. First of all, we had a hard time finding a proper controller. Eventually, we found the one that we needed for our spec, but we had to go through a lot of research. The second and the main problem that we had was to get a stepper motor for our steering control. And the one we were considering was out of our budget. It was around $3,000. So we had to come up with something cost effective. And we came up with a 12-volt DC gear motor, and that met our budget. So we went along with that. The disc brake, as Mike mentioned, we used electromagnetic drum brake. Electromagnetic was to be used, but it was too expensive, and it's mainly for industrial purposes, and they normally sell for more higher prices. So we went along with drum brakes, which was implemented, they showed. The motor, as we actually discussed earlier, we were first initially using the 500 watt 36 volt DC motor. After we added all the weights of the battery and the framing and everything, we were having a hard time getting it because there was no differential. So every time we turned, it didn't have enough power to overcome that. So we had to replace the motor, and we bought a 24 volts, 1.1 kilowatt motor, and that gives enough power to play around with, and we overcame the problem that we had with the motor. Cost analysis. Majority of the money we paid was for the controllers and the motors that we bought. The drum brake was in our budget, but the labor costed us so much. Also, as I mentioned, the rear motor. The batteries were, we bought some batteries, but then school donated some after that we needed actual batteries, so that was in our budget. Also, the limit switches were kind of expensive. They were for the safety purpose that we used. We could have gotten for cheaper, but we had no other sources here, so we had to go with that. Other thing we had, as I just said, the controller. The diodes were okay. The final cost came up to $35.50, but this doesn't include the controller, the new motor. But we were donated two controllers that were $800 each. That have been donated by Lance Motor Control. So this cost was being rounded down.
And here's the final product. As you can see here, these are the two main cutoff switches. So if anything were to happen, anything wrong would go wrong, you can just switch them quickly off. There's a steering wheel with the buttons that Nilesh was talking about to activate the steering, brake, and drive. There's our batteries, the pedals, the limit switches, and there's the new 1.1 kilowatt motor and batteries right there. Two controllers that were donated also right there in the back. And that's the final project right there. Here we're going to show you a little video of how it runs. Here you can see the headlights turn on. Pedro is driving. We also have a brake light in the back. We estimated that the drive was actually 20 miles per hour. Here's another example of this technology drive-by-wire system by BMW. As you can see here, BMW is actually automatically parking by itself by sensors, electronic sensors. Other advanced technologies can be used, such as wireless control, GPS. These are all the benefits of these drive-by-wire systems.
A few people that we would definitely have to give thanks to. We did get a lot of help in getting this project implemented and getting it to the stage where it is now. One person that I definitely have to give thanks to is my father, Dominic Condello. He helped us with a lot of the welding and a lot of the mechanical things that we would have otherwise had a lot of difficulty with. We're not as experienced in we can do the calculations, we can do the math. When it comes to actually getting in there and welding something onto a frame, that's something we're a little bit inexperienced with, and he definitely did give us help, and he deserves the credit. As well, the SVSU, the Cardinal Racing team, being sort of working close with them in the Pioneer Hall, they did give us a lot of mechanical advice, and they helped us machine some parts as well. And they sort of kept an eye on us as we were working and gave us pointers as we were going along. Dr. Mohammed Al-Kasabi gave us a lot of guidance throughout the design process for the control systems. And we definitely went to his office quite a few times for help in that respect. Dr. Russell Clark was our supervisor on this in this project, and he did give us a lot of insight into the safety requirements. Every week we would have a meeting with him, and he would give us a lot of what-if scenarios. What if the driver is driving and this happens? What are you going to do to make sure that the driver doesn't die? And there was a lot of what-if situations that could, theoretically result in the driver getting injured, and we had to take those things into consideration. So he did give us quite a bit of help in that respect. Dr. Chris Schilling provided us some additional funding for the batteries we needed for the new 24-volt motor, and he was generous enough to provide that funding for us. And as well, the company Advanced Motion Control donated two $800 controllers that were used. We did have a few other choices at the time, but the AMC controllers were our first choice. They were the best suit for our particular situation. Unfortunately, they were out of our budget, but the company did step up and donate them for us. And was there any questions?
You have separate batteries for your steering controller motors and for your propulsion system?
We do. We considered originally running all the systems off from one power supply. There was a few disadvantages. There's an obvious advantage because you only have one power supply rather than two separate ones. But we did find a few advantages to going with two separate power supplies. Number one, safety. If the drive system, if the 24-volt drive system for some reason loses power, you've still got the 12-volt power system that controls the steering. So they're completely independent of each other. If one fails, the other could still operate. And as well, the power ratings, to get a 12-volt battery that would drive the rear wheels would draw way too much current, and to get a higher voltage motor that would operate the low RPMs that we needed to run the steering, it would have been a difficult match. So going with a low voltage system for the steering and a higher voltage system for the driving system seemed to be a better result.
If the power supply for the brake and steering failed, would that automatically cut out the propulsion system?
The drive, yeah, automatically.
Even though they're on separate power supplies?
Absolutely. As well, there's buttons right on the steering wheel. If the driver inadvertently shuts off either the steering controller or the braking controller while the vehicle is in motion, that will automatically shut off the drive controller as well. If you shut off the steering while you're driving, the steering shuts off, the drive shuts off, but the brake stays enabled because you may still want to brake to a stop. And that also goes if the steering signal is somehow lost. If the wire is cut, or for one reason or another, the propulsion will shut off, but the braking will stay active. Is there anything else?
Did you have any feedback to the steering wheel to oppose you when you turn the steering wheel? Give you a tactile feel for where you're turning?
We left the steering wheel that we chose. There was a few different wheels that we were considering. One of the ones that we were considering, we discarded the idea because if you turn it and you let it go, it would spring back to its initial position. And since the controller will continually track the position of the steering wheel, that would cause oscillations in the output. And as well, this steering wheel had force feedback built into it. We didn't implement it, but the force feedback motor is in there. So by software, that force feedback motor could be programmed. If there's a disturbance, an external disturbance, it could be programmed to feel that feedback into the steering wheel.
Based on either calculations or testing, do you have any idea how long you could drive the car between charges?
We estimate while we were testing, in the testing phases, we would drive it for like 2 or 3 minutes, take it back in, run a few tests on it, maybe the next day run it for another few minutes or so, maybe 10 minutes. So it was hard to get an accurate description of how long it would actually last. The steering motor, the 12-volt battery right in the front that controls the steering motor, we actually just charged it for the first time since we bought it a few days ago. And actually, we had to leave it overnight with a headlight, an automotive headlight plugged into it just to drain it because since we bought it, we were waiting for it to drain and it just wouldn't drain. But of course, we do understand that the rear drive motor does draw a lot more current, and that one would run out faster. We estimate probably about an hour or two that it would last from a full charge. As well, another thing that we wanted to keep in mind, we wanted to make sure if both the front and the rear power systems were fully charged, and you drove it until one or the other ran out, we wanted to make sure the drive system would run out before the steering system, so that way you wouldn't lose steering control due to a voltage drop. So yeah, to answer your question, about an hour or two.
Now, is braking is the same power supply as drive, right?
Yes.
So if you were to run out or start to run down, would it, I mean, how much more current does it draw? Say if you were driving for a while, would you still have enough, or would it reach a certain point?
Yeah, the braking system requires a lot less current.
Yeah.
To stop the car, you maybe need about 4 or 5 amps, whereas to drive, you need about 60. So you would definitely run out of power in the propulsion long before you would in the braking.
Did you measure the transfer function of the motor when you're doing the control system?
We ran into some trouble because of the load. One thing we actually found out after we started doing some of the implementation that depending on the surface that you have the wheels, the motor operates quite differently. The controller has PID settings that drastically affect the response of the controller, and depending on what type of surface, for example, when we first got it up and running, we had the car propped up, and it responded a certain way, and then when we put it back down on the ground, it sort of responded, it didn't really respond the same way, so we had to adjust our gain settings accordingly. But in terms of doing the calculations, it was more, because of the nature of the controller, it's all software programmable as a piece of code. It was mostly done by trial and error. And actually it was done quite